It's fairly easy to oxidise a primary alcohol to an aldehyde without over-oxidising it to the acid. Numerous reagents have been developed for that very purpose, and I've demonstrated one of them in a previous video. What's not so easy is to selectively reduce an acid derivative to an aldehyde, in other words to approach the aldehyde from the other direction. The method cited in textbooks is the Rosenmund reaction, a catalytic hydrogenation of acid chloride using a poison palladium catalyst with reduced activity. This is not generally accessible to amateurs because it involves high-pressure hydrogenation, which needs specialist apparatus and a source of hydrogen gas, plus palladium compounds cost an arm and a leg. Another method is reduction of acid chlorides with sodium borohydride at minus 78 degrees, which is the boiling point of dry ice. Again, this is impractical for amateurs and not completely reliable. It works on the basis that at such a low temperature, the reduction from an aldehyde to an alcohol is much slower than the reduction from an acid chloride to an aldehyde and doesn't actively prevent it. It also suffers from poor yields. In my quest for an amateur-friendly procedure, I came across an interesting variant on the borohydride reduction published by Babler in 1982. This reaction was carried out around 0 degrees, used sodium borohydride and also a large excess of pyridine to capture any borane present and prevent the aldehyde from being reduced to the alcohol. This method, with some modifications, is the one I'll be demonstrating in this video. The acid being reduced to an aldehyde is salicylic acid. In a previous video I demonstrated how to reduce this to salicylic alcohol, with the ultimate goal of converting it to salicylic aldehyde, but I found this method was more elegant. The first step is to convert salicylic acid to salicyl oil chloride. I've gone over the method of turning acids into acid chlorides in detail in my last video, so other than detailing the improvements I've made since then, I'll keep this short and sweet. The reagents used were salicylic acid, 13.8 grams, cyanuric chloride, 18.4 grams, THF, 75 grams, acetonitrile, 50 grams, triethylamine, 10.5 grams, and perchloroethylene, 50 grams. Salicylic acid and cyanuric chloride were dissolved in THF, diluted further in acetonitrile, and triethylamine was added dropwise. Once addition was complete, the mixture was left to stir for 2 hours, then it was filtered by vacuum. Most of the solvent was removed from the filtrate by distillation. The distillation was stopped when around 40-50 ml of liquid-solid mixture remained, and it was clear that the solvent was boiling off entirely from the surface. The marshmallow-like solid mass that remained was mixed with perchloroethylene and shaken thoroughly. The extract was filtered by vacuum twice and cooled overnight in the fridge. In this case, the product itself can't easily be isolated, as it has a tendency to react with itself and polymerise when the solvent is removed, resulting in tar. The original paper used carbon tetrachloride to isolate the acid chloride. This is hard to come by, but perchloroethylene, which is used in dry cleaning and is chemically very similar, is much easier to find and produces excellent results. I didn't have this when I made the original video. It's possible that better yields could be achieved by refluxing the mixture instead of shaking it at room temperature. From the smell it was clear that some of the product was still entrained in the remaining solids. A further limitation of this reaction is that if the starting acid chloride contains a long hydrocarbon chain, it's likely to be soluble in PCA, carbon tetrachloride, as well as the acid chloride, and depending on the nature of the acid, the final product could potentially be very difficult to separate from the starting material. The next step was the reduction itself. The acid chloride is added as a solution in perchloroethylene. The purpose of the pyridine is to capture any intermediate borane as a pyridine-borane adduct, which is insoluble in perchloroethylene and can be removed by filtration. The aldehyde is then isolated in the workup. The reagents used were salicyl oil chloride solution in perchloroethylene, sodium borohydride 3.8 grams, DMF 40 grams, THF 25 grams, pyridine 12 grams, deionized water 2 grams, talcum powder, 20% hydrochloric acid 50 grams, sodium metabisulfite 28.5 grams, potassium carbonate 28 grams, DCM 3 portions of 15 ml, and sodium sulfate. Sodium borohydride was dissolved in DMF. Once it was dissolved, pyridine and THF were added to the mixture. While this was happening, the acid chloride solution from the previous step was filtered by gravity into an addition funnel, removing any unreacted acid. The borohydride solution was moved to an ice bath to keep the temperature under control, as this reaction is very exothermic, and the acid chloride solution was added to the borohydride solution dropwise, making sure to keep the temperature under 20 degrees. Once addition was complete, the solution was mixed for another 45 minutes, and all visible gas evolution had ceased. Deionised water was added to the mixture to destroy any unreacted acid chloride, and then it was filtered by vacuum through a 1 cm layer of talcum powder. Because talcum powder doesn't let much of anything through, this took around an hour. As a result, the pump was pulling a pretty tight vacuum, and when I switched the pump off and didn't disconnect it from the filter quickly enough, some suckback occurred and the filtrate became contaminated with a few mils of brown hydraulic oil. The nature of this procedure means that this unexpected addition was annoying but not disastrous. Any unreacted borohydride impurity in the mixture was quenched by adding hydrochloric acid, which caused the mixture to heat up and foam vigorously, nearly spilling over the top of the beaker. Once it had cooled down, after about an hour, I separated the perchloroethylene hydraulic oil layer from the aqueous THF-DMF layer using a funnel, then mixed the non-aqueous layer with a 35% sodium metabisulfite solution for half an hour. This was separated into 2 phases using the funnel. The aqueous phase was neutralised with a 40% potassium carbonate solution, then extracted with 3 15ml portions of DCM. Because I was working with such concentrated salt solutions, DCM became the top layer, which took me by surprise at first. These were dried with sodium sulfate and filtered, then the solvent was removed by distillation. The final product, salicylic aldehyde, was a slightly yellow oil, noticeably denser than water, with a high refractive index which didn't have much of a smell on itself, but left behind a distinctive smoky sweet smell wherever it had been. The yield was 1.68 grams, which is 15% overall with respect to salicylic acid. And let's be honest here, that kind of yield is frankly terrible. On the plus side, the reaction works and is reliably reproducible, but on the minus side, in its present form, it's inefficient. It needs a whole cocktail of reagents and organic solvents in order to be carried out for not much return at all. The main source of uncertainty is that the yield from the acid chloride reaction is unknown because the product can't be isolated and I've got no easy way to determine the concentration of it in solution. It's mixed with a known amount of PCE and an unknown amount of THF and acetonitrile, which makes estimating the concentration from the overall density or refractive index of the solution very difficult. The reduction step has been modified from Babler's original method, and most of these modifications are a result of scaling up the procedure. The original method involved cooling the borohydride solution to 0 degrees, then adding the acid chloride all at once. On the scale I've carried it out, this is extremely exothermic and causes the solvents to boil, which is why the acid chloride was added dropwise and the reaction mixture was kept in an ice bath to keep the temperature under control. I also found it was not necessary to cool the mixture to 0 degrees. In the original method, a hexane diethyl ether mixture was used to remove the pyridine-borane adduct from solution. When I used diisopropyl ether instead, 2 layers formed, and this made workup more difficult. Because I don't have diethyl ether, it's very expensive to transport, and in pain to store because it's the solvent equivalent of Houdini. This method used PCE instead, achieving the desired result, and allowed the reduction to be chained onto the end of the acid chloride reaction. In the original method, the mixture was run through a fluoresol column to remove the insoluble pyridine-borane adduct. Silica can't be used because it's acidic enough to release borane from the pyridine-borane intermediate, which over-reduces the product to the alcohol. Fluoresol costs an arm and a leg, and since I'm not being funded by public money and I don't work for a university, I don't have the money or the means to justify buying it just for use as a filtration aid. Instead I bought some reagent-grade talcum powder, which is chemically similar and much cheaper equivalent. This performed exactly as expected. Babler's original workup was a simple acid-base extraction with copious use of brine. I added the metabisulfite extraction step in order to extract aldehydes and nothing else, but it seems in this case the adduct is not very soluble and a substantial amount of aldehyde is left behind in the organic phase, so a less concentrated solution may work better. In summary, this method delivers what it promises. It reduces acid chlorides to aldehydes near room temperature in a reliable manner, but in its current form it needs a lot more work to get a decent yield out of it. I hope you enjoyed this video. Thank you for watching.